Thanks for making it. I'm Satya Ramachandran. I'm the VP of Engineering for the Marketing Analytics Group at Neustar. What I'm going to be focusing on is on some objectives and principles for building predictive models on big data. We've been building a predictive analytics platform targeted towards marketing the past 8 to 10 years. So most of this is coming from our experience building it. And again, this is just one point of view of how we came up with a solution. I'm hoping that this becomes an interactive discussion that just is not in this talk, but we can continue even after the talk is over, right? Because clearly this is something that is at the forefront of analytics, and it's going to be in the forefront for a long time to come. Make sense? I wanted to talk about the problem that we are solving, but before that, I just wanted to take an example, a personal example. So I wanted to buy a shirt. Actually, the shirt I'm wearing right now, I wanted to get a shirt. I saw an ad on the TV. It sounded very interesting, and I happened to be near a computer. So I went to the website. I was then looking at, okay, fine, what kind of shirts did this company offer? Because it seemed very trendy. Then I even took a couple of shirts, put it in the shopping cart, and then I said, okay, this is too expensive. I went away, right? And then the next 10 days, I visited Facebook, or you go to any site that company's ad was always in front of me. That did not affect my sale. I was never actually prompted. I mean, that didn't get me there. Then one fine day, I was walking on Union Street. I saw the company store. I said, okay, this sounds interesting. I've been looking at it for some time. I walked into the store. I tried on a few shirts. I still was not interested. I walked away because the shirts were a little expensive. And then a month later, I got a bonus. Now suddenly I have some extra cash. And then, and lo and behold, a week later, I get this email which offered me a 20% discount. Right? So finally, I took the leap. I went there, took the 20% discount, bought the shirt. So clearly, it is every purchase is a complex journey. And what we do is we do multi-touch attribution, where what the multi-touch attribution does is to allow marketeers to credit multiple marketing causes along the user journey, right? I want to go slowly, just to kind of illustrate each one of those points. The first thing is the credit of all the sales. Where did the sale come from? Which aspect of the marketing or whatever you can control contributed to the sale? Ties it to the various causes. And I'll go into more detail as we go along the talk. And the most important thing, and the reason why this is becoming extremely interesting right now, is today everything is addressable. We can track it. We can track the fact that I watched a TV ad to a reasonable extent. Track the fact that I visited the website. We can even track the fact that I went into the store and I clicked on the email marketing. And therefore, a marketeer can make a much more informed decision where to spend the money. And that's what we do. We create these attribution models, and then we allow marketeers to decide how they should spend their marketing budget. Make sense? And then, this is like getting a little bit deeper. This is a standard analytical cycle. Before I go, how many of you in the audience are in analytics or are implementing analytics or a consumer of analytics? Okay. how many of these is is predictive versus reporting? And does that make any sense when I say predictive? I see 3. That's great. And what I'm going to be talking about is, again, hopefully to you and to everybody else, kind of make a distinction between predictive and, more importantly, see an aspect which I think is not well served in the industry, talk about it, and then talk about the solution that we came up with, right? And together, maybe we can learn something new. Make sense? So this is an analytical cycle. I just want to go very briefly. I'm sure this is being talked about quite a bit. At the far end, in an analytical cycle, it always starts with data. You bring in data, you process data on top of it. In a predictive modeling environment, once the data is processed, you then break it down into features, and we'll talk about that more in the talk. After that, you create models on top of these features. And once the models are created, you use these models to then go and predict how the outcome would be in the future, right? That's the complete cycle. And most of this is reasonably well understood today. What I'm going to be focusing on in the next part of the talk is not creating the models, not running the scoring of the models, but actually, once the models are created, how does the end user use it to effectively make decision? So this is something, the whole scenario analysis, once a model is created, and how do I then use the model to come up with the decision is not well discussed, right? Execution of the models is not well discussed, is my opinion, and that's what I'm going to be focusing on. Fair? So to kind of break it down, I created a simple example, and then I wanted to use the example to further talk about what do I mean by execution or scoring of the model. This is a very simple star schema. You have data which we call fact, and that fact has a number of impressions. We would call that like display impressions. This is ads that you see. The spend on those impressions, and then the Google query volume, right? This is the three. This is the data that you have, and then that data is available by product, right? This is a gaming company or something, and then by time, by quarter. Every quarter you have this data, and then by geography. These are the states. Okay. Now, reporting on top of such kind of data, even with high volumes, is well understood, right? Even the last decade, you can have much more complex analysis on top of this historical data. Not only can you create dashboards, you can also do some clustering analysis, segmentation, and so on. And that is well understood. But what if I say, okay, now that you have this data, in the third quarter, you have the first 2 quarters of data. In the third quarter, if I increase my spending by 10%, what will be the impact on the Google query volume, right? Those are the kind of questions a predictive model addresses, where the data is not found, where there's a gap. Uses the model to address this. To answer this question, you can easily compute the spend, right? You can have some heuristic rule to compute the spend. You can just take the second quarter's worth of data, or third quarter's worth of data, and then you can do some numerical calculation to say that. Or you can take it from your plan, and you can say, this is my spend. However, like I said, the Google query volume is actually something that is not under your control. Right? It happens because you do certain activities, like the purchase that I did on the store. For that, you need to build predictive models. What happens behind the scenes, and again, this is a very simple example. Clearly, it's a lot more complex in thing, is the fact that first, to build the models from the data, all the modeling algorithms work only on flat data. That's how it is. The entire data is denormalized, or it's flattened out. Then, what you do is you kind of build these features, right? In this case, and I have a section where we talk about feature engineering a lot more. You build these features. In this case, there are two features. The first feature is product impressions, right? It's nothing but the number of impressions which are by product on TV, right? Number of TV impressions by product. And then the other one is the spend on the product, local product spend. And of course, you have the outcome variable, which is the Google query volume, right? So you come up with a set of features, and then you assemble it in an equation. Here, it's very simple. You have just two variables. So you kind of put them in whatever equation form that you want to. Here, it's a simple equation. This could have all kinds of forms. You can multiply them. You can have another complex function or something like that. You put them in an equation form, and then the outcome variable is obviously a result, and then these two are the contributing variables. And then you have something called that C1 and C2. These are the coefficients, right? In this additive equation, you're trying to estimate what the coefficients are. So you estimate the coefficients, and as you clearly notice, it's not a single value, it's actually a vector, right? For each one of those things, variables. You then put it in a matrix, and I can go into the details of how this happens. You put them in a matrix, and then every calculation is a matrix calculation on top of that, right? You take the input coefficients, then you get the output. Just to illustrate that with an example, for the same thing, for the same example we talked about, increase of 10%, you've gotten all the new values for the spend, right? Then then you multiply them by 10%, because that is the whole, you have a spend. You multiply them by 10%. Then you put them in the matrix here. That's the new local spend that you have. You multiply that with the coefficients, which you got in your equation. You then get the corresponding Google query volume. You then take it back to your data, and then you aggregate it, and you finally get the predicted Google query volume. Right? What is the problem? I mean, this is it seems to be reasonably simple in terms of, okay, once you've created the model, all you have to do is to extract the variables, put it in a matrix, and then multiply with the coefficients and get the resultant value. The challenge is this is an actual customer example, right? This is a retailer, and that's the kind of data that you're typically working on. It has about 10 dimensions, different cross sections, and then it's got all kinds of metrics, right? I talked about purchases. You can go and look at clicks. You can go look at spend, revenue. You can look at click converting rates. So there are so many outcomes that you can actually go and predict. Similarly, from an input, there are so many variables that you can operate on, right? It is a huge volumes of data, so many experiments that are possible, right? And that is where scenario analysis becomes a lot more difficult in this modeling environment. I know that there are a few people who work who said that they do predictive models. Can you talk about your experience on when you create a model? Like, what do you do with the model? Like, once the model is created, what happens to them?
So right now, what we're trying to do is some sort of operationalizing or productionizing the models. So one of the cases, I work for FedEx, so one of the things which we are using here is for route planning. So we are going back into the historicals to pull, to see what the route plan was to, so compare the today's route plan with the historical to be able to come up with a delivery time window, which you guys usually get either text or on your delivery manager, you will see that if your packet is supposed to come today, is it coming between 8:30 and 12:30? So that's the time frame. So we're trying to get to that 8:30 to 12:30. So we're trying to predict based on current today's route, and then what was our historical, plug the traffic on top of it and weather on top of it to predict what is going to be the delivery window for a particular shop.
Understood. So these are like, there is a model, there are specific inputs that is present in the model, and there's a specific output, and as long as you plug in the input, the model predicts the output. What if you wanted to do something else? Then you'll have to go through the entire modeling cycle. You have to create a new model, you have to create a, I see, okay. And that's what becomes tougher, right? Like, so once you have this data and you have numerous things that you want to look at, and pivot table analysis for reporting is standard. You don't like, once you build a pivot table, then you can do any kind of reporting and any kind of analysis. But unfortunately, in a predictive world, that kind of flexibility does not exist, right? And that's what I was trying to illustrate with that example, that only when that happens, the enterprises would start actually going and using it. Go ahead.
But how can I don't know if it's possible that you don't go back to the beginning, because as soon as you introduce a new data point,
Correct.
you introduce potential correlations with other data points, which then will adjust and
Correct.
it's an
Correct.
system.
That's a fair question, right? But please remember that this is a very typical enterprise data warehouse schema, right? Enterprise data warehouses are very good at managing their metadata and to allow changes to come in. So let's assume that first of all, you have something like this. This is standard, right? For any big, like, Fortune 100, Fortune 500, Fortune 1000 company, to have a reasonable schema which doesn't change as much. You're not going to. So look at the dimensions there: time, marketing driver, non-marketing driver, product geo, publisher, campaign, tactic, creative, placement. No magic about it. These are all standard dimensions, right? Even if you go one level down, if you look at all the locations, it's not going to change that much, right? Even two levels down, the dimensional values, the actual values, do not change much. I do agree that new values get introduced, but that's not the problem. The problem is here in FedEx, there is an enterprise warehouse. They do have data, a lot more data than what they're solving. But every time they need something new to be analyzed, they create a model, right? And then that model can only predict, take only input for what that model can predict. In this case, can you repeat what this is just predicting when the packet would arrive, right? Yeah, as opposed to where would be the demand for these packets or something like that, right? Which is an adjacent problem, but you would have to go through that entire cycle, right? And that is why I don't know if the decisions that are taken at the enterprise level are still using the predictive models, which is the right way to go about things. Does that make sense? Or? Yeah, okay. Okay, okay, sounds good. And we can go into a lot more details, but to build this, there is a math aspect of it that I want to get into. How do you build these generic models, right? That is a topic for another time. But I can talk about what we did from a computer science, from an engineering perspective, to make sure that these can run better, right? We've had tremendous successes. When we first started out, way back, is we used to have like very small number of variables. These are like this decision points, that one cross section that I showed in the previous one, right? We had 130 million cross sections. This is one. These are one cross section. So we had 1,200 cross sections, about 2 million data points. I don't have the numbers here, but it used to take us, from what I remember, it used to take us like a couple of hours to actually go and run a simulation, sort of, right? And then we reduced it by just engineering from V2 and V3 to a substantial amount. By V3, we were able to run it in seconds, right? Now, we are able to take an entire enterprise class schema, and that leap from V3 to V4, we are able to run it in sub-seconds, right? And how did we get there? The first step was all software optimization. Like I said, to run these predictive models, you had to first have the matrix, right? You had to create the matrix, right? So what we would do is we'd pre-create the matrix, and then if there are any changes to the source, we would use logs to replicate the changes to the source. So whenever I need to run the math, the matrix was always available for us, right? That was our first insight, right? Here I'm assuming that the math, for some reason, for that particular problem, magically appears, right? This is just the execution of the math, of the model. So that's the first thing we did. And that, obviously, when we had the math and we had to run it, the data was already available, so it solved a lot of that input problem. Then the second thing that we focused on, and this is all the V2 and V3 optimization, was then the read. When you're reading these matrices, and I'm sure, for a real predictive model, for us, we had 2 million, 3 million rows for every model, and that would take a reasonable amount of time to get there, right? Seconds, if not whatever the reads and write. So we would make sure that we would only read. So there was a lot of configuration that we did where we only read what is required. And similarly, if you notice in my example, once after you read it, you still have to take the output, and then you have to normalize it so that it can get back to the reports. Same thing on the right side, we make sure we optimize it. These are all simple. I'm sure anybody who's going through something like that, this is the first thing they do, right? There's no magic about it, and we did get some amount of optimization because of that. The biggest optimization we got was we started recognizing that the math, just like you have an application, and the application has an ER schema, right, and an ER model, and that is how it gets represented. You have objects, and and that is how enterprise applications get run. Math needs to get married to this enterprise ER application model, right? This is where, once we did that, we were able to not only optimize the read and write of the variables of the matrix, not only optimize writing it back to the disk, we were able to create these models, right, at any scale you want to, and we were able to run them. So the schema that you talked about, we were able to materialize these models under certain constraints. We can run these models, and then we can actually go and produce these results. We are not solving any problem, by the way. We are only solving adjacent problems. For example, we are only solving attribution, right? In attribution, we are only answering questions. We can answer questions at the national level. We can answer questions at the state level. We can answer questions at the zip code level, or we can answer questions at the individual level. Same questions. Or we can answer questions only on the product. What happens when the product spend changes? We can answer questions only on the channel, marketing spend, and so on and so forth. You can change your input wherever you want to. For that particular algorithm, we're able to run it, and we're able to produce results almost instantaneously. Common modeling approach. across all of these levels. And then the model itself, we are able to materialize it for that particular cross section. Let's say you have product. You're saying, I'm not interested in any other thing. I'm going to just look at product. I'm going to change the distribution of product, and then can you tell me how the attribution is going to work? And if I increase the product spend, what happens? We're able to materialize that model at runtime. Or you can say, now, I'm not interested in product. I'm only interested in media. So I'm going to say, how is my media spend? And I'm going to change the media spend. At that time, I don't go through an extensive modeling experience. I can just go back to my thing, materialize the model necessary for the media, and then run that model and produce the results. So I think ours is a parametric model, right? Clearly, right? I am not aware of any. I mean, that's where we started off. I'm not aware of any non-parametric approach.
So you're just making one gigantic data set that can feed any model.
Correct. Correct. A star schema, which you can ask like a pivot table analysis, except that the answers in a pivot table analysis is just doing simple aggregations or whatever. Here, you can create your view, and then you can run predictions on top of it. There'll be a model that it materializes and runs. And clearly, this is a deep topic, and I understand that we are on the forefront of it. I've been talking about it for the past 4 years. I don't see a lot of conversation around here, but I do see this as an emerging field, right, which is going to be the last mile in taking predictive models and having them applied to enterprises. Let me focus on something else, feature engineering. We talked about features. So I'll talk about what do we mean by features, and what did we do to again scale feature engineering within our company. Okay. Going back to my example, I want to set the context again. So you have here 3 aspects, right? You have the cause, which is what is causing you have the cause, and then you have the conversion, which is like, actually folks, actually people buying the thing. And then you have the end user. Cause is what is making sure the effect happens. I have a 10-minute morning. Cause is what making the effect happen. And what ties it all together and what is relevant is the user. And this could be, the cause could be many things. It could be something under the control of the marketeer, which is like, my marketing spending. Or it could be, the price of the fuel in terms of a car company, right? Or the weather, right, in terms of like, an insurance company and so on and so forth. Or things which are completely, weather would be an example on that, where it's not under my control at all, right? Like whatever, I'm not even able to understand. So it could be all kinds of causes which leads to an effect. And in our world, obviously, like, we have different type of these events. I'm going to be using this color coding quite a bit during this conversation. So here I have like, color, each one of these color codes are the segments that are there, right? So I have like, I think about 5 here, and each one represents the channel, the media channel in which the marketing event occurred. But you could actually have a lot more categorization of this. Consider this as an attribute vector, right? So I could start out the channel. You could have a sub-channel, which could classify the problem a little bit more, or you could have a tactic. It's entirely up to the modeler or the data scientist to be able to choose at what level do you want to start looking at the problem. There are other aspects associated with it. You don't want to look at the entire data. You might want to look at a subset of data. It could be a simple filter. It could be a much more complex filter, right? You might only want to work at Mondays, for example, right? Or that could be another filter, which is not like a simple linear filter, and so on and so forth, right? And then, like I said, our problem is once we have identified the data, then we want to look at each one of those features, and we want to see how that contributed to revenue. What the claim is, once you have created a system which make sure these kind of concepts are formal in your processing. You could create a very generic data processing system that could be applied to a wide variety of problems. You don't have to custom code generating these features. Okay. And hopefully, I'll get to show that in the next few slides. So again, I'm taking it back. I'm keeping it simple, just the channel. And here you have 5 different types of channel. And that was just one, but in real world, it's a very complex environment. The sequences are not simple sequences. You could have some of these exposures could be exposed to multiple people, and then some of them could be directly targeted towards a person and so on. So in our case, we can actually take this and come up with a very generic processing using very simple 3 simple steps. The first thing is to just break it down, right? So that you have a unique attribution across all of these users. The next thing is to then go and take that categories that I talked about, and then group them along the categories. And then the next thing is to then go and apply any kind of a numeric function that you wanted to apply. To illustrate, this is one of the functions that we use. It's called the hazard transform. I forget what the G stands for. It takes each one of those events, calculates the lag for that event, takes the minimum value, and then applies that formula on top of it, right? And that predicts this hazard transform predicts how useful that particular event is for the effect. One of the measures to understand how useful the event is for the effect. So and you can do that for any number of these functions, right? And this is generic. It's got nothing to do with the schema. You can just have it generic. So what do you need to do to get there? The key principles are, first thing is, when you're doing data definition, right, you need to separate the logic from the data itself. The schema itself should be irrelevant to what you are actually going and processing. For example, let's say you have the hazard transform, right? In that hazard transform, there's a calculation which is 1 over 1 over x. That should be independent to whether it's been applied to media, channel, and so on and so forth. That should be, the data itself should be irrelevant. In this complex world, then you have to allow for the data to come in. We saw that in the previous slide. The modeler could have chosen a channel, could have chosen channel and subchannel, or could have chosen something else. The attribute vector constantly keeps changing. So you need to allow for granularity as well as flexibility in terms of adding these dimensions. You need to allow for other cross-cutting considerations, right? Like look back is a consideration, all kinds of filters is a consideration. And then more importantly, when you're devising something like this for feature engineering, you need to be able to allow for logic to be added at runtime. I should be able to come in, even if I didn't have that function, I should be able to come in and add that logic at runtime, and then I should be able to run it. Our goal is once today our system is running entirely using configs. We don't write code. We don't write SQL code to generate the features. It's entirely done by configs. Our goal is for them for not to even write that configs, but use metadata to actually generate the configs. And so what we have is we have a monitoring system which maintains the statistics, and we have now started using those statistics to start predicting what kind of configs do people need. And we've done quite well. These are actually the hours for the same thing. Different personas. The personas that we are interested in is, for example, data management. These are the SQL jockeys who sit in and who write the code to materialize the thing. And then even the modelers or the data scientists hours, where they are trying to decide between various features. Over a period of time, we have substantially reduced the amount of time both for data management and the modeling, when the complexity of the problem had increased, our goal, which is like, very soon, is to eliminate them completely in the modeling pipeline in the future, right? In the presence of the data science or the complexity increasing quite a bit. So I'll stop there, and I have more details of how exactly we did what we did. I had another topic, but clearly did not plan very well, which was on the reporting subsystem. But I'll stop right there, and I'll take any questions, comments, concerns.
So when you rebuild a model using time-based data, sensitive, snapshots of data, how do you get that same performance, or how do you map the data set such that you're not sort of exponentially exploding the number of things available to you, or the layers of time-sensitive data that are available to you? Seems like you have to do transformations at least on some pull,
Correct.
right, if you want to add in these time lags.
Correct. So that again, so that is where I think the metadata comes in. So in our case, if you look at the features, the metric itself, like a GHT is one aspect, the dimension is one aspect, the time lag itself is another aspect of it. These are all configurable parameters from our system. So you can actually go and say, look at time lag, and you can vary the time lags. You can say like last 1 week for example, the has-been before variable and so on and so forth, right? How many variables do you actually go and choose for estimation, right? That is the machine learning or the feature selection problem, right? Here, what I'm talking about is more of the engineering of once I decide that these are the variables you need to create, do I write SQL code or just write the configs, and then the code gets generated and you materialize the feature set, right? And we produce an exhaustive feature set. You can have like 100 features, or you can have like 1,000 time lags. You can have 20,000 time lags on your modeling set. The algorithm that our modelers use to exactly extract what kind of features I want, they use genetic algorithm as a way of isolating what features are needed. That is one method. Most of it is heuristic, because I'm in the retail industry, I'm in the insurance industry. I understand like what time lags are important, and then I actually apply my heuristic to do that. So it's a combination of both. First is the filtering based on my industry experience, and then the next thing is to then start using. We use genetic algorithm, some kind of a feature selection mechanism. But once you've selected the feature, this is more about materializing that set of features to run your estimation and scoring.
Well, with that many features, how do you know you don't have confounding factors, considering all these types of engineering that you're capable of doing and retaining, and then allowing any other modeler to walk in and just pick from the bucket? The confounding factors that you don't want to have. You don't want to have data leakage, right? You don't want to have your predictors already have your response data embedded into it in some transfer.
Understood. So I think this is more about how predictive the model is, or what is your feature selection correct, and how do you understand whether the feature selection itself is correct, and so on, right? We'll talk about it, and clearly this is assuming that those things are taken care of. This is just being able to materialize a feature. Like you have your enterprise warehouse, and you want to materialize a feature set. It's how fast you materialize the feature set without writing code. But exactly whether the feature set itself is valid or not, there are different techniques that we follow, but that might be very specific to attribution and so on.
Do you have any ideas on the design of the feature set?
Say that again.
Do you have any ideas to design the feature set? So you said so there is many heuristics of the designing feature sets, but I don't know how do we do.
I see. So in our see, our problem is pretty simple, right? So because our problem is we focus on attribution. We're focused on a specific problem, so we have come up with a bunch of rules as we look at the marketing funnel for each one of these activities, right? What combinations of these features are interesting, right? And so that is our first level filter. And then once we apply the first level of filter, the problems, the search space becomes a lot lesser, and then then apply like a GA algorithm to go search within that space. And those heuristics are all like, marketing attribution specific. So, so it is those preliminary rules that you have to apply, right? And again, something like let me ask you this question: like, are you a modeler? She's probably a modeler, right? So when you want to like do a modeling exercise and you want to create that data set, what happens? What's a typical journey?
To correct, I'm not a modeler.
Okay.
I have the entire data analytics environment responsibility.
Oh, I see.
So I have business users who would come to us with their use cases. I do have the data scientists to help out with the modeling. What I've seen is that we have to do research on the features that are done, work with business users quite closely, understanding the problem of which features are those effective features which can be.
Understood. And after the research on the features are done, how are how do you get the feature set? Like how does it get materialized?
Are you talking about getting the data for it?
Getting the data for it.
Yeah, so then we engage our ingestion team to get that data in. But again, it could be in a Teradata, we have an EDW,
Correct.
or it could be in Oracle databases. We have Adobe ClickShare also. So there's just different various ways to get that model data in.
Understood. And that
Scoop is usually used for.
understood. Understood. And that kind of custom programming environment, as opposed to here, where once you have a feature set, you create a config, and then you're able to materialize the data set without running like writing any code or whatever, right? Being able to materialize it is what this talk is about, and is essentially establishing those feature set. That's kind of a math modeling problem. I'm sure we can touch base offline and talk about it. Okay. All right. Thank you.